You ever stop and think about how we actually train an AI? It really does feel like magic sometimes, right? We just throw a bunch of data at it, let it cook for a while, and then suddenly it can write a poem or tell you if that's a cat in your picture. But what is actually happening in there? How does it learn? Well, let's pull back the curtain.
See, at its heart, training a neural network is really just a massive optimization problem. It's like trying to solve a puzzle with, I don't know, millions or even billions of pieces. The space of all possible answers is unbelievably complicated. So here's the big question that baffled researchers for years. If this puzzle is so incredibly hard, why do our methods, which are often surprisingly simple, work so well?
To even begin to wrap our heads around this, we need a map. So I want you to imagine the entire training process as a journey through this vast, imaginary, high-dimensional terrain we call the loss landscape. Now, on this map, every single setting for the network's parameters is a point, and the altitude of that point? That's how wrong the network is. It's the error, or what we call loss. So the goal of training is simple. Find the lowest point. Find the deepest valley in the entire landscape.
Okay, but this journey, it is not a gentle walk in the park. For the early pioneers of AI, especially when they started trying to build really deep, powerful networks, this descent was absolutely treacherous. The landscape was just filled with hidden dangers that made it almost impossible to get anywhere.
And there were two monsters in particular that lurked in this landscape: gradient explosion and gradient vanishing. These two problems were so bad that for the longest time, making networks deeper actually made them worse. The training algorithm would just completely get lost.
And you can see the problem right here. In some parts of the landscape, it's almost perfectly flat. That's a vanishing gradient. Your algorithm takes a step, but the ground is so level it has no clue which way is down. It's totally lost. Then in other spots, you've got these sheer cliff faces. That's an exploding gradient. You take one tiny step, and whoops, the algorithm goes flying off the cliff, completely overshooting any good solution that might have been nearby.
So, how in the world did we ever conquer this terrain? Well, we developed a toolkit. Think of it as a set of essential gear for any deep learning explorer. And these aren't just little tweaks. They are fundamental techniques that actually reshape the landscape itself, making it way, way easier to find your way down. This image gives you a great sense of the modern approach. You can see how these smart design choices, our tools, give us real advantages. Things like starting in the right place, or having the right gear to control the steepness of the terrain, or even building bridges. All of this helps speed up the journey and leads us to much better valleys. So let's check out a few of these tools. So, our Explorer's Toolkit really boils down to three key pieces of gear. First up, proper initialization. This is all about picking a good starting spot on the map so you don't begin your journey teetering on a cliff edge. Second, normalization. You can think of this like having really good hiking boots, making sure every step you take is stable. And third, skip connections. These are amazing. They're basically like building magical bridges to bypass the most dangerous parts of the landscape altogether.
So let's talk about that starting point. Instead of just parachuting our explorer randomly onto the map, we use these really clever initialization schemes, like Xavier or Chiming. They're designed specifically to place our starting point in what we call a good basin. You know, a relatively smooth, bowl-shaped area where the path down is pretty clear right from the get-go.
Okay, next up, the gear. Even if you start in a good spot, the terrain can still be super slippery. That's where normalization techniques come in, especially the famous one, batch normalization. They work constantly during the descent, rescaling everything. The best analogy is that it's like putting on crampons. They just give the algorithm solid footing so it can take bigger, more confident steps downhill without slipping and falling.
But even with a great start and a steady footing, a huge problem remained. As people tried to build deeper and deeper networks, the models would just get lost in this increasingly rugged terrain. And this was so weird, because a 50-layer network would often do worse than a 20-layer one. It made no sense, and it was a massive roadblock for years.
The solution was a total game changer. It was an architectural breakthrough called ResNet, and it introduced something called skip connections. And the idea is so simple, it's beautiful. As information flows through the network, some of it goes down the normal complex path. But a skip connection creates a second path, like an express lane, that just hops over a few layers. It's literally like building a bridge over a treacherous canyon. It gives the signal and, just as importantly, the gradient, a super clear, easy path to keep the journey going.
So, with this amazing new toolkit, we basically became expert navigators of the lost landscape. But as we got better at exploring it, we found something really surprising. The map, the one we thought we were navigating, it was kind of wrong. The landscape wasn't at all what we had feared it to be.
And this gets us to what is maybe the core insight of modern deep learning. For most of these gigantic networks, the biggest challenge isn't getting stuck in a bad valley forever. No, it's the journey itself. It's getting over the cliffs and through the flatlands. That's the really hard part. The destination, it turns out, is less of a problem than we thought.
So you see, the old fear was about getting trapped in one of countless bad local minima, these little valleys that weren't the true lowest point. But the modern reality? It's more about efficiently navigating these huge flat plateaus called saddle points and just avoiding the steep cliffs. The challenge isn't about ending up in the wrong place, it's about making the journey there efficient at all.
And on top of all that, researchers found this wild property called mode connectivity. It turns out that in these crazy high-dimensional spaces, the good solutions, those deep valleys we're looking for, they're not just isolated little islands. Nope, they are often part of these vast, interconnected basins. What that means is, if you can just find one good solution, there's probably a whole highway of other equally good solutions connected right to it. Finding a good solution is way more possible than we ever dared to imagine.
So it seems like we've pretty much figured out how to navigate, right? We've got the maps, we've got the tools, but looking at neural networks as just an optimization problem, well, it doesn't quite explain everything. It actually leaves us standing on the edge of a whole new mystery.
So let's just quickly recap. We now get that even though the landscape is incredibly treacherous, our modern toolkit, from smart starting points to architectural bridges like skip connections, has turned us into expert navigators. We can reliably, consistently find the low points. And that, right there, is the fundamental reason why training these ridiculously complex networks actually works so well.
But here's the final and maybe most important question. Our map shows us lots of different valleys, and they're all at a very, very low altitude. Our tools are good enough to get us to any one of them. The thing is, we found that some of these valleys give us models that are brilliant in the real world, while other valleys, just as deep, give us models that aren't. Why? Why does one low point generalize to new data so much better than another? Well, that's the other half of the puzzle, and it's the next great landscape for AI researchers to go out and explore.